Hello, we are Josue, Adan, Crisostomo, Carreño, and Oscar Adame Vazquez. We are going to talk about Chapter 9, Subnetting Networks. In this chapter, you will learn why subnetting can be necessary in a network, as well as how you are expected to manage the subnets for different types of devices or services. You will learn how to create the appropriate subnet mask for any subnet required. You will also learn how to appropriately determine the best subnet configuration according to the required number of networks and hosts, and if the use of a variable length subnet masking is required, and how to do it. Subnetting an IPv4 network. In a small network, a flat network design is not problematic. However, as the network grows, this type of configuration can create major issues, as increased traffic slows down the overall performance of the network. Larger networks must be segmented into smaller subnetworks, keeping them localized to smaller groups of devices and services. The process of segmenting a network by dividing it into smaller network spaces is called subnetting. Devices and services can then be grouped into subnets determined by any kind of organizational division that makes sense for the network. Subnetting can reduce overall traffic and improve network performance. A router is necessary for devices on different networks to communicate. Traffic that is destined for a device on a remote network will be processed by the router and forwarded towards the destination. To determine if traffic is local or remote, the router uses the subnet mask. Subnetting creates multiple networks from a single address block, and each subnet is treated as a different network space. Devices on the same subnet must use an address, subnet mask, and a default gateway that correlates to the subnet that they are part of. The size of the subnet involves planning the number of hosts that will require IP host addresses in each subnet of the subdivided private network. The private IP address range used on a LAN is the choice of the network administrator and needs careful consideration to be sure that enough host addresses will be available for the currently known hosts and for the future expansion. Knowing your IP address requirements will determine the range or ranges of host addresses you will implement. Subnetting the selected private IP address space will provide the host addresses to cover your network needs. Two very important factors that will lead to the determination of which private address block is required are the number of subnets required and the maximum number of hosts needed per subnet. Each of these address blocks will allow you to appropriately allocate hosts based on the given size of a network and its required hosts currently and in the near future. IPv4 subnets are created by using one or more of the host bits as network bits. This is done by extending the maps to borrow some of the bits from the host portion of the address to create additional network bits. The more host bits are borrowed, the more subnets that can be defined. For each bit borrowed, the number of subnetworks available is doubled. For example, if one bit is borrowed, 2 subnets can be created. If 2 bits are borrowed, 4 subnets are created. If 3 bits are borrowed, 8 subnets can be created, and so on. However, with each bit borrowed, fewer host addresses are available per subnet. As shown in this image, the IP network has 24 bits in the network portion and 8 bits in the host, indicated with the subnet mask of 24 bits. Notice that only the host portion is indicated in bits, as the rest is indicated in decimal number. With no subnetting, this network supports a single LAN interface. If we want an additional LAN, the network will need to be subnetted. So in this image, one bit is borrowed from the most significant bit in the host portion, thus extending the network portion to 25 bits. This creates 2 subnets identified by using a 0 in the borrowed bit for the first network and a 1 in the borrowed bit for the second network. The subnet mask for both networks uses a 1 in the borrowed bit position to indicate that this bit is now part of the network portion. Now in this image, when we convert the binary octet to decimal, we see that the first subnet address ends in 0 and the second ends in 128. Since only the most significant bit was borrowed from the host portion, the 2 subnet addresses change by 128, and the subnet mask change for each subnet is indicated by the last octet 128. Using the 2 subnets created in the last example, we now have the next configuration. So notice that the router R1 has 2 LAN segments attached to the gigabit Ethernet interfaces. The subnets will be used for the segments attached to these interfaces. to serve as the gateway for devices on the LAN. It's common practice to use the first or last available address in a network range for the router interface address. So the first subnet is going to be attached to the interface 0, and the second subnet is going to be attached to the interface 1. To assign an IP address for the PC1 and PC2 and other devices, it is necessary to determine the range of valid IP addresses for each subnet. The guidelines to consider when determining IP addresses are the next. The network address is represented by having all host bits on 0, while the broadcast is all bits on the host portion in 1. The first actual host address is simply the network address with a 1 on the least significant bit of the host portion, which is just the next address, while the last host address uses the broadcast address with a 0 on the last bit of the host portion, which is the previous address from the broadcast. Following the subnet guidelines, this is the address range for the first subnet IP, and this is the address range for the second one. To configure the previous network, the gigabit Ethernet interface 0 uses the next address that follows the network address of the first subnet, and the interface 1 uses the next address of the second subnet. The PC2 uses the second host address available for the second subnet for its IP address, with the same subnet mask and the interface address set on the router for the default gateway. To calculate the number of subnets, the next formula is used. And to calculate cost for each subnet, you use this formula. For example, 2 raised to the 7 power is 828 hosts, but 2 of them are not available for the host assignments, so you only have 126 host addresses. So in this example, borrowing one host bit towards the network results in creating 2 subnets, and each subnet can have a total of 126 hosts assigned. So this is 2 subnet network, and if you want more subnets, you need to do the same steps seen before. For example, to reach subnet network, you need to borrow 2 bits, and you will be able to have 4 subnet networks because 2 times 2 is 4, and you will have 62 IP hosts because 2 raised to the 6 power minus 2 is 62 hosts for each subnet network. Now imagine you want to build a 100 subnet network. So with the previous example, you must borrow 7 bits to have 128 subnets, but now borrowing 7 bits will leave you just one remaining host bit, and if we apply the host calculation formula, the result will be no host on the subnets, because if you calculated 2 raised to the first power, it's equals to a minus 2, you end up with 0 hosts. In a situation requiring a large number of subnets, an IP network is required to have more host bits to borrow from, such an IP address with a default subnet mask of 16 bits. There are 2 considerations when planning subnets: the number of host addresses required for each network and the number of individual subnets needed. Notice that there is an inverse relationship between the number of subnets and the number of hosts. The more bits borrowed to create subnets, the fewer host bits are available. Therefore, fewer hosts per subnet. If more host addresses are needed, more host bits are required, resulting in fewer subnets. Every network within an organization is designed to accommodate a finite number of hosts. Basic subnetting requires enough subnets to accommodate the network while also providing enough host addresses per subnet. It also has to be taken into account the fact that the number of hosts might increase in the future. Some networks, such as point-to-point WAN links, require only 2 hosts. Other networks, however, such as user LAN in a large building or department, may need to accommodate hundreds of hosts. Consider the example of a corporate internet network that must accommodate several number of hosts across different locations. In this example, the service provider has allocated a network address with 10 host bits. This will provide 1022 hosts, more than enough to accommodate the addressing needed for this example. Considering that there are 5 LANs with 4 inter-network connections, we require at least 9 subnets available, for which we will have to borrow 4 bits from the host portion, since 2 raised to the 4 power is 16 subnets. and 6 bits will remain for the host addresses for a subnet. Notice that the largest LAN contains 40 hosts, and 2 raised to the 6 power minus 2 will result in 62 host addresses, so there will be enough space for every host in the nice subnet. Each subnet address will vary by 64, so the final scheme of this network should end up like this. Determining the number and size of the networks. Always consider the number of subnets and hosts needed for each subnet. Take on account that in a corporate network you might want to consider the growth of the network or number of subnets. In this exercise, we are required to make a subnet with a certain number of hosts and formulate an appropriate subnet mask that meets the requirement. For example, if we need 1,000 hosts, we must borrow 10 bits from the hosts, which result in a total of 1,022 possible hosts, and we would use the subnet mask of 22 bits. In this case, we get 4 LAN subnets and 3 WAN subnets. With traditional subnetting, 3 bits are borrowed from the host section to be able to create 8 subnets, each with 30 hosts, which should suffice for this kind of network. However, the 3 WAN subnets only require 2 hosts to properly work, and leave 28 host addresses unused. So even when traditional subnetting can work, it can also be really inefficient in this case, leaving in total 84 host addresses wasted. For this kind of a scenario, variable length subnet mask can be used to avoid wasting addresses. As shown in the next example, traditional subnetting creates a fixed number of subnets with equal number of usable hosts, and each subnet makes use of the same subnet mask. With variable length subnet mask, you can divide a network scheme in unequal parts, and the mask will vary depending on the borrowed bits. From the previous example, in which was required 4 subnets for LAN and 3 for WAN interconnection, as it's only 2 addresses are needed for the interfaces on the WAN, many addresses were being wasted. Variable length subnet mask can be used in this case to avoid this waste and create more subnets. In this case, the last subnet will be subnetted. Since we want 2 usable host addresses, 2 bits will remain from the original 5 host bits, and the other 3 will be borrowed to create a subnet from which 3 will be taken for the WAN addresses and the other 5 will remain available. After doing this, the LAN addresses will remain the same, using 27 bits for the subnet mask, and the WANs will end up using 30 bits. Addressing schemes. There must be 3 considerations to take account when determining address allocation. Preventing duplication of address. Each host in an internet network must have a unique address, providing and controlling access. Servers must provide resources to internal and external hosts. If the address is randomly assigned and not well documented, controlling access is more difficult. Monitoring security and performance. Security on the network itself should also be monitored. Network traffic should be examined for addresses that generate excessive traffic. With correct planning and documentation, problematic network devices can be easily found. Assigning addresses within a network. There can be different types of devices within a network: end-user client, server and peripherals, hosts that are accessible from the internet, intermediary devices, and the gateway. So when developing an IP addresses scheme, it is recommended to set a smart pattern for each type of device. This process should list any future modification in the network, like adding or removing devices. A network addressing plan might include different range of addresses across subnets for different types of devices. Addresses for clients. Usually Dynamic Host Configuration Protocol (DCHP) is usually preferred on large networks to reduce the burden on network staff and eliminate errors. Another benefit from using DCHP is that IP addresses are only temporarily assigned to a host, so if the subnetting scheme needs to be changed, there is no need to reassign host addresses individually. Only the DCHP server will need to be reconfigured with the new subnet information, and the host addresses will be automatically assigned. Addresses for servers and peripherals. Network resources should have a static IP address, especially since PC hosts access these resources through their IP address. Addresses for hosts that are accessible from the internet. Only a few devices are usually available for access to hosts from outside the corporation. These devices should have a static IP address as well. Servers should also have a unique public address associated with them. Generally, you want this kind of devices to have predictable addresses. Addresses for intermediary device. Almost all traffic between and within networks goes through intermediary devices. Usually, these devices are great to establish security and network management. These devices also need a predictable address so it's possible to communicate with them. Addresses for the gateway, routers and firewalls. Routers and firewall devices usually have interface IP that goes through different networks. These interfaces work as gateways for hosts. The router interface uses either the highest or the lowest address available, and this assignment should be consistent across all networks of a corporation so the gateway address is always known. These devices are also used for security as all traffic that goes from or to the network must pass through them, so they can be used to filter packets based on source or destination IP. Subnetting an IPv6 network. IPv6 subnetting requires a different approach than IPv4 subnetting. The primary reason is that IPv6 there are so many addresses that the reason for subnetting is completely different. An IPv6 address space is not subnetted to conserve addresses, rather, it is subnetted to support hierarchical, logical design of the network, while IPv4 subnetting is for about managing address scarcity. IPv6 subnetting is about building an addressing hierarchy based on the number of routers and networks they support. IPv6 address block with a 48-bit prefix has 16 bits for subnet ID, as shown in this figure. Subnetting using the 16-bit subnet ID yields a possible of 65,536 subnets and does not require borrowing any bits from the interface ID or host portion of the address. Each IPv6 subnet contains roughly 80 quintillion addresses, obviously more than enough that will ever be needed in one IP network segment. Subnets created from the subnet ID are easy to represent because there is no conversion to binary required. To determine the next available subnet, just count up in hexadecimal. As shown in this figure, this means counting by hexadecimal in the subnet ID portion. The global routing prefix is the same for all subnets. Only the subnet ID quartet is incremented for each subnet. Similar to borrowing bits from the host portion of an IPv4 address, with IPv6, bits can be borrowed from the interface ID to create additional subnets. This is typically done for security reasons to create fewer hosts per subnet and not necessarily to create additional subnets. The best practice is to subnet an enable boundary. Enable is 4 bits and hexadecimal digit. As shown in the figure, the 64-bit subnet prefix is extended 4 bits or 1 nibble to 68 bits. Doing this reduces the size of the interface ID by 4 bits, from 64 to 60 bits. Subnetting a nibble boundary means only using nibble-aligned subnet masks. Starting at 64, the nibble-aligned subnet masks are 68, 72, 76, 80 bits, etc. Subnetting on a nibble boundary creates subnets only by using the additional hexadecimal value. In the example, the new ID consists of the 5 hexadecimal values, ranging from 00000 through FFFFF. That will be all for this chapter. Thanks for watching.